Sir, should we start or we take a couple of minutes?
I think we should start because people have joined, I think, by YouTube, other people.
So, with due respect to our today's distinguished speaker, Professor Rajiv Asthana of Department of Engineering and Technology, University of Wisconsin-Stout, and I welcome all the participants, those who are there in the Microsoft Teams, and those who are watching the live streaming of today's distinguished lecture through YouTube. Today's distinguished lecture is been organized by Indian Institute of Metals Rourkela Student Chapter and National Institute of Technology Rourkela. So this is a part of the National Institute of Technology Rourkela's Diamond Jubilee celebration, and so we have a year long of distinguished lectures. So this is a part of that, and so with these few words, I request Professor Anand Basu, Head of the Department of Metallurgy and Materials Engineering and National Institute of Technology Rourkela, to say a few words about Professor Rajiv Asthana. Sir, over to you, please.
Am I audible?
Yes, sir.
Thank you, Professor Patra. So I think really privileged to introduce Professor Asthana. So this is the onset of the Diamond Jubilee year of the department, and the institute is already celebrating the Diamond Jubilee year. So on this gracious occasion, I'd like to welcome Professor Rajiv Asthana. He is a professor of Department of Engineering and Technology at the University of Wisconsin-Stout, USA. Previously, he also worked as a researcher at NASA Glenn Research Center. He is editor of various testing journals, Society for Materials, and received several awards, including Distinguished Engineering Educator Award from the Engineers Council, Dean's Outstanding Alumni Award from College of Engineering and Applied Science of University of Wisconsin, and NASA recognition and award. His research interest includes joining of ceramic metals, ceramic brazing, metal matrix composite, etc. So, and we are organizing this series of talk on the jointly by the department, the Diamond Jubilee organization body of the institute, and also by the Indian Institute of Metal student chapter of the Rourkela body. And with that brief introduction, I will not take much more time, and I would like to request Asthana to take the charge. And today's the topic of his talk is high temperature capillarity in liquid phase bonding of metals and ceramic. So, Professor Asthana, please.
Okay, thank you very much for the introduction. I'm glad to be here. Good morning, everyone. Evening for you. So it's a morning here. I'm here in Cleveland, Ohio. I teach at the University of Wisconsin, and I'm spending my summer 3 months here at Cleveland, Ohio for some research on joining of materials. So I thought I would speak about a topic that is related to the joining work I do, and it is high temperature cap in liquid phase bonding of metal to ceramics. So I'm going to look at some of the work that I and some of the colleagues overseas have been doing in this area. Just as an introduction to the place I work at, this is the eastern and Midwest part of the United States. This is the Atlantic Ocean over here. Let me pull up the pointer. And the state of Wisconsin is right here towards the northern part of the United States, North Midwest. And the city called Menominee is right on the western edge of the state of Wisconsin. And this is our campus here, aerial views of campus situated on a lake. The university is basically the only so-called polytechnic university in the state of Wisconsin. In Wisconsin, we have several different universities. The state university system is called the University of Wisconsin system. Madison and Milwaukee are the two major campuses, flagship campuses, and then we have 12 other campuses of University of Wisconsin, and Stout is one of them. We have very comprehensive career-focused programs and our employment of students has been very, very good for last several decades. So with that, let us get back to the topic here. So what are the areas impacted by the considerations of high temperature capillarity? These are some of the areas that are affected by this topic, melting and casting technologies. So for example, in investment casting or single crystal growth, interaction between the mold materials and the high temperature alloys is important. In melting technology, holding crucibles, electrodes, filters, and all kinds of ceramic materials come in contact with high temperature liquid metals. So again, capillarity and reactions are important. Brazing and diffusion bonding, metal matrix composites, sintering, and many other areas are affected by this topic. So it's kind of a highly applied area of research, but it has some very important fundamental ramifications. And I'm going to look at some of those in this talk today. So I'm hoping to finish my discussion in about 40 to 45 minutes, and then I will open it for discussions and questions from students and audience. So we all know about metal composites, ceramic metal composites. You're basically trying to join either fibers of a ceramic or particulates with a metallic matrix. So it's again a joining case. Actual brazing and bonding involve macroscopic or large bulk specimens to be bonded to one another with a metallic or non-metallic interlayers. So these are the areas that we consider. Here are some other examples in which I have been working for last several years. In joining, we looked at some of the NASA's fuel injector system where we were trying to join silicon carbide discs to low expansion Kovar tubes. So these are fuel carrying Kovar tubes, and these are perforated silicon carbide discs through which air would flow. And these had to be joined together either by brazing or diffusion bonding, and also the Kovar tube had to be joined to silicon carbide. So that was one system we looked at. We created heat exchanger elements. This is just one unit where you have titanium tubes carrying a fluid that is bonded to high temperature carbon-carbon composite sheets and supported with highly conductive porous carbon foam. So these kind of elements are stacked and joined to create a heat exchanger. So we were looking at just the basic materials science part of joining here. We looked at solid oxide fuel cells where you have a steel interconnect to be bonded to, let's say, zirconia, YSZ kind of a ceramic material. And then high temperature systems, silicon carbide composites joined to either to themselves or to other materials. Also high temperature diboride based materials. And then silicon nitride joining to Inconel and similar alloys for turbine application. So those were some general areas. I'm going to look at liquid phase bonding here in this talk today. So brazing is my focus here. And the concept in brazing is very simple. You take a joining material, which is basically some sort of a glue, metallic or glassy glue, and you melt it and then bring the two surfaces together under a very small pressure. The melted braze will spread over the surfaces, and upon cooling, excuse me, the surfaces should bond. So two key areas in this kind of a process are wettability, the problem of wettability, that is the liquid should be able to spread and bond to the surfaces. That's one aspect. And then because of expansion mismatch between the surfaces, there is quite often a lot of residual stress that has to be managed in some way or the other. So in my talk today, I'm going to look at mainly the wettability part in high temperature systems. The question is, why study high temperature capillarity, which is also called wettability? It's a very old, much researched topic. So what is the purpose of doing additional research on that? Well, there is a lot of data that is available, but very few data have high precision. The experimental process is very difficult. It's not easy to conduct these kind of experiments because the conditions for experimentation have to be very stringent. Even under vacuum in your furnace, you are oxidizing the liquid metal, and that could interfere with the spreading process. So we will see some results on that. And also, there is no standardized procedure for characterizing the wettability of systems. So we don't have any ASTM or ISO or other kinds of standards. And that is one of the challenges we have in studying high temperature systems. For low temperature liquids like water or organic liquids, there are a lot of commercial units available. Optical tensiometers, as they're called, or goniometers, very simple devices that give you the wettability or contact angle data, but you don't have any system like that for high temperature systems. And that is the reason that we have some special needs here. So here is an example of a simple system, pure aluminum melt in contact with aluminum oxide. And if you look at the literature data on contact angle versus temperature, you see numbers all over the place. And even with a small superheat, when you are somewhere here, look at the scatter in contact angle data, somewhere from 85 degrees all the way to 165 or 170 degrees. So, and that the reason for that is that these kind of measurements are extremely sensitive to testing conditions, to material preparation, and other things. So, in fact, in the classical literature, contact angle has been used as a probe to study surface and interface phenomena. Now, low temperature systems are much easier to examine than high temperature systems. And that's why we need some special devices to study high temperature interaction between liquid metals and solids. So here is a unit that was designed and built by one of my good colleagues, Dr. Natalia Sobczak, and in Poland. This is a high temperature wettability measurement unit, probably the only of its kind in the world. It allows a variety of things to be done in this chamber here under very high vacuum. You can actually manipulate the liquid droplet, and we are talking about 1 to 2 millimeters diameter droplets. You can manipulate droplets inside the vacuum chamber. You can move the droplets, open up interfaces, and you can also analyze the gases coming out of this chamber for the chemistry so that you can work back the kind of reaction that might be taking place. So those issues are not critical in low temperature systems that have been studied in many other areas, but high temperatures present unique challenges. So just for a moment, going to the basics for some of the students who may not be familiar with the topic, when you have a liquid droplet, a very teeny droplet that you bring in contact with the solid surface, the liquid spreads and then it stabilizes. And typically, if you have, let's say, water on a clean glass slide, it will take a few microseconds for droplet to stabilize and give you an equilibrium shape. For high temperature systems, the liquid droplet will keep spreading for half hour or an hour or more. And that is mainly because of the reactions and interactions that take place between the liquid and the solid. So the angle of contact is basically defined as this angle between these different interfacial tensions that occur at surfaces or interfaces between different phases, liquid, vapor, and gas, liquid, vapor, and solid. So all of this formalism was developed more than 100 years ago for low temperature systems, and the same concepts are being used for high temperature systems, although not very effectively because of these unique challenges. reactions, oxidation, surface roughening ahead of the spreading droplet, evaporation and condensation of the liquid ahead of the droplet in the vacuum chamber. So the surface gets modified while the droplet is spreading. So those kind of things, some of those things we looked at. Here is an example of a nickel droplet on a chromium coated aluminum oxide substrate. And what we see here is that during the testing process, there is evaporation and condensation of nickel vapor on the surface here, and it forms some little teeny eutectic droplets of nickel chrome over which this larger droplet is spreading. So these are very, very complex systems as compared to the low temperature systems. And roughness of the substrate, the chemical inhomogeneity of the surface, all these things will influence how the liquid spreads and interacts with the solid. Sometimes the spreading process is not uniform or homogeneous. You have anisotropic spreading, so this side of the droplet spreads differently than the other side. Even in a simple system, like if you have a steel, ordinary steel, a liquid will spread differently on, let's say, cementite and ferrite areas or other types of inhomogeneities. So it's quite challenging when you have high temperature systems. Another example, aluminum carbon. A teeny liquid droplet of aluminum in contact with the vitreous carbon substrate. There is reaction, aluminum carbide formation, and these crystals form ahead of the liquid droplet. So the droplet is actually encountering a rough surface when it is spreading. In the nickel aluminum system, when nickel aluminum droplets spread on magnesium oxide, there's reaction and magnesium spinel forms like whiskers ahead of the droplet. In aluminum silica system, for example, there is reaction between silica and aluminum oxide forms, and there is volumetric expansion, which again causes cracking and roughening. So here is an example of how we study wettability in some systems. We are looking at aluminum droplets spreading on aluminum oxide substrate with nickel phosphorus coating on it. So these were the tests done in Poland. And you can see that the liquid melts and begins to spread on the surface here. Now, if you did the same kind of an experiment in an environment where oxide film forms on the droplet, the oxide prevents spreading of the liquid on the surface. And you can see this here. Are you able to see the movie? I'm just checking it. Can you see that clearly?
Yes, sir.
Okay. So look at how this 2 millimeter droplet is spreading, and this oxide skin is preventing the spreading of the liquid underneath. So when you have situations like these, if you measure the contact angle without understanding what is happening on the surface, you get incorrect data. And here is another video clip that shows what happens to the oxide skin when you go to high temperatures. It will dissociate and allow liquid to spread more homogeneously. I think for some reason my video clip is not. See if I can make it run here. You see the oxide that broke off on the droplet, and you can see the camera reflection very clearly. And remember, all these experiments are being done under fairly high vacuum. Even then, the droplet is getting oxidized, which is not unexpected. And once again, if you take a look here, you will see the oxide breaking. You see here the little particles break, and it becomes a cleaner droplet. So these kind of experiments allow us to study the liquid metal solid ceramic interactions in more depth. And if you look at the data on different substrates, here we're looking at pure aluminum droplets spreading on aluminum oxide, silicon nitride, boron nitride at different temperatures. And we are plotting the equilibrium contact angle. That means the angle when the droplet has stabilized its shape. So when you look at the data, pretty much in all substrates, there is one temperature close to 1000 degrees Celsius where the contact angles are all the same. So the angle does not depend on the substrate up until this temperature. What that means is that up until this temperature, oxide skin on the liquid droplet with the spreading process. Above about 1000 degrees Celsius, you can see that the contact angle on each substrate is different. And that is what we expect also. So in the system that we study, there could be reactions taking place between the liquid and the substrate. So the reaction layer could grow at a rate slower than the spreading of the droplet. When that happens in a system, the liquid is contacting the original virgin substrate, not the modified surface. You also have systems where the reaction product grows faster than the liquid spreading. And in this case, liquid spreads on a modified surface. The reaction layer may not be just a single homogeneous reaction product. You can have multiple reaction products. And you can also have situations where the reaction product layer is porous, mainly because of volumetric expansion or due to some sort of cracking, which would cause the liquid volume to change. Here you're looking at liquid copper, silver, titanium droplet on a carbon-carbon substrate. And we did some wetting test on carbon-carbon, and we saw obviously a lot of liquid being lost by penetration of the porous surface. Even in sintered aluminum oxide substrate, we see reaction layers forming between copper, silver, titanium braze and the substrate. So this is the reaction layer, but we also see some infiltration of the substrate. So in all these cases, the volume of the liquid is continuously changing because of infiltration and reaction, and that is going to change the angle of contact that you measure. So in many cases, the measured angle in high temperature systems is not really a thermodynamic angle. It is more of a practical indicator. So most wetting tests are done using what is called a sessile drop method and using a contact heating process. So the idea here is that inside the vacuum chamber where you have the furnace, you put the solid sample on a solid substrate and then heat them together until the liquid melts and begins to spread. And then you can image continuously the spreading process. And from that, you can determine the contact angle. The problem in this kind of experiment is that you have no way to control the reactions or interactions taking place while the solid samples are getting heated. And also, it is difficult to time, beginning time for interaction between the liquid and the solid because the melting process is not obviously instantaneous. So because of these challenges, this kind of a contact heating is not the best method. A better method is what we call capillary purification process, where you squeeze a liquid metal out of a high purity aluminum oxide capillary. So you heat the metal separately inside the vacuum chamber and you heat the substrate again separately in the same chamber. And at some specific time, you squeeze the liquid droplet, bring it in contact with the substrate. So this kind of a process does many things. One, it allows you to have an accurate estimate of time of contact of the liquid and the solid. Two, that you are not heating the two things together until melting, so you can actually see the reaction between liquid and solid, not the reaction that takes place during heating of the solids in contact. And the third point is the most critical one. That is, when you squeeze the liquid out of the capillary like this, you are actually eroding or destroying the surface oxide film. So this gives you a more accurate measurement of contact angle. And this video shows what happens. You are squeezing the liquid droplet on the surface of the ceramic and then allowing it to spread without any oxide skin causing any problems here. So if you look at the data of contact angle with time, contact heating gives you the same contact angle values at 1273 Kelvin that you obtain by this method, even at 973 Kelvin. So even at low temperatures, you are able to get the correct contact angle that would be possible in contact heating only at very high temperatures where the oxide will dissociate by itself, either by dissolution in the liquid or gaseous suboxide Al2O formation and other things. So this is the case of aluminum on silica. You can see the same kind of behavior with other systems. So when you look at aluminum on aluminum oxide and you run different experiments using capillary purification, where you're actually squeezing the droplet out of a capillary, and compare the contact angle values with the value that you obtain by contact heating of aluminum alumina, you can see the effect of removing the oxide film. Again, at low temperatures, you are able to get very, very clean surface and low contact angles that are not possible at fairly high temperature in contact heating kind of a process. And these are some data that show what happens to the bond strength of the joint in a system like that. So we are looking at aluminum droplets on titanium substrates, and we looked at experiments where we had capillary purification process and also contact heating process. So for these two types of sessile drop test, we let the test run, then solidified the droplet, and then we bisected the droplet assembly and did shear tests. Based on those, we estimated the shear strength or bond strength. So this is the bond strength versus the displacement of the droplet during this kind of a test. And these are the contact angle data with time for contact heating systems, and the red one is for the squeezing the droplet out. So because we were able to remove the oxide skin, we got very high bond strength in the system, even at 1173 Kelvin wettability test. And even at 1373 Kelvin, contact heating did not give you that level of bond strength because the contact was not very good. Interference from oxide caused this problem. Some of the tests we did were on composites because my interest has been in joining ceramic composites to alloys. And obviously, because of the inhomogeneous surface of ceramic composites, even after polishing and cleaning, you see that the spreading process is not very homogeneous or uniform. And the droplets spread anisotropically, not nice circular fashion, but in a more anisotropic fashion. So again, we measured contact angles by contact heating. Also, some capillary purification methods were used. In most cases, we see a good wetting, mainly because our brazes were all reactive brazes. But from a fundamental point of view, none of these angles is actually the young contact angle. It is, again, a practical indicator. One process we use is drop suction. You can actually lift the drop from the surface and open up the interface, and then study the interaction between the liquid and the solid. So after some time, you can lift the droplet, open up the surface here, cool it, and then see what kind of interactions took place as a function of time. We are also able to manipulate droplets in the chamber. You can slide the liquid droplet on one surface. So this droplet was here. We pushed it, opened up this area, and then we can examine it upon cooling, what kind of interactions took place. So these kind of things allow us to control the time of interaction accurately between the liquid and the solid. But you can imagine these kind of experiments are extremely difficult to conduct, mainly because you're trying to manipulate teeny liquid droplets inside a high vacuum system in a chamber where you are continuously heating the systems here. So you could do this kind of pushing of droplets either when you have this capillary purification process or when you have this contact heating. And if you look at this slide here, you are pushing this liquid droplet, and this is actually the nickel tungsten droplets on magnesia 100 substrate here. And what you see is that even though the system is non-wetting, the droplet wants to come back to magnesium oxide. There is good adhesion, even though the contact angles were kind of low. I'm sorry, contact angles were high, so it was a non-wetting system. So those are some of the things that normally we don't consider. We think that if the wetting is good, adhesion will be good. If wetting is poor, that is contact angles are large, the bonding will be poor. That's not the case always. Here we are looking at some of the droplet displacement results. So again, this is magnesium oxide surface, and we have nickel tungsten droplet that was on this side, and the droplet was pushed to open up the surface here under the droplet. So this is actually the triple line, which was the liquid boundary between the free surface of MgO, and this side was under the droplet. And we are able to, these are AFM images where you can actually see the surface underneath the droplet. What we saw was that the bigger liquid droplet, which was about 2 millimeters in diameter, up into little droplets, kind of a daughter droplets, and those droplets actually reside inside these little dislocation edge pits. So when you push the droplet on the surface like that, the teeny micrometer sized droplets, they actually break off from the mother droplet and they get stuck in these little dislocation pits. These are some results on liquid aluminum droplets on aluminum oxide, polycrystalline and single crystal. These are single crystal. So we push the droplet and now you're looking from the top. So this is the area where the droplet was sitting earlier. And you actually see some aluminum oxide crystals forming under the droplet after the droplet was pushed away. And obviously, alumina is so-called non-reactive system, but because you have dissolution and reprecipitation taking place, these little aluminum oxide crystals form. We see the same behavior with polycrystalline aluminum oxide substrate. So this is looking from the top after pushing the droplet away and opening up the surface underneath, and you do see these little crystals that formed, aluminum oxide crystal that formed from dissolution and reprecipitation. Several other types of tests can be done. I will not spend time showing these, but you can actually shear the droplet during the squeezing process, and that allows you to study how clean oxide-free liquid will contact a moving surface. Here you're looking at a system where the wetting, the contact angle was poor, but again, the adhesion is good. So this ceramic is actually lifted up when the liquid solidifies because the contact was very good. Here we are looking at this kind of a system. You have aluminum oxide on which you had a solid piece of aluminum, and this is the quartz silica transparent silica plate. So inside the vacuum system, when you melt aluminum, you can actually see through the silica quartz how the liquid is spreading and how the reaction layer is forming. And then later you can actually do actual chemical analysis and microscopy to see what phase is formed. But this kind of real-time visualization is interesting because these quartz plate of silica allow you to see through the region and study the reactions between aluminum and silica. The same thing is being done with multiple silica plates where you had aluminum on the top. So you're melting aluminum and allowing it to infiltrate the gaps between these quartz plates, and you can actually see the liquid propagating and how the reaction layer is forming. And after cooling, obviously, you form some quench cracks. Another effect that we see is some sort of a dancing of metal droplet. In low temperature systems also, this has been seen, something called camphor dance. Camphor liquid droplets actually dance around on the surface. We see something similar in high temperature systems. So if you look at this video, you will see that there is wetting and de-wetting process taking place. And after some time, the droplets will begin to bounce and jump around during the heating process. And the reason for that is little gas formation here. So look at the bubble, the droplet, it is moving around on the surface. If you go back and look at this area, this is during the heating process, and we are looking at very long times, 200 minutes, 230 minutes of contact time. So this kind of a process takes place mainly because under this 2 millimeter droplet, you have these teeny gas bubbles that evolve either from reaction or from degassing of the substrate, and they cause the bubble to dance around. Here you're looking at the system where you have, shrinkage, solidification shrinkage, showing its effect. So when you heat the system, the plate, this is magnesium aluminum oxide plate, it comes down when you are heating the thing because the liquid is expanding. You can see it coming down here because of expansion, but the adhesion stays very good between the two. And when you cool, the liquid will solidify and the magnesium spinel plate will actually be lifted off because of the capillary forces here. And we see these effects even in systems where there is no wetting, but the bonding is good. So now the plate is lifted because a good bond has formed. There are changes in the surface of the substrate. So initially the substrate might be flat when it is in contact with the solid metal in the vacuum chamber, but as the reaction takes place, the volumetric changes from reaction will change the shape of the substrate. It becomes more convex. You can see here in this example, it is solid droplet or solid piece of metal that is going to melt. The surface is still more or less flat, but as the liquid forms and react with the surface of the substrate, you will see the surface becoming more and more convex. And so these kind of tests allow us to actually see in real time what is happening between liquid that react with the solid. And you can see how the surface has actually changed from flat to fairly convex. So I think with that, I will just summarize the main points here. My idea here was to just share with you, with students, some of the interesting things that are not commonly examined, even in simple systems. So we are able to actually study complex functions under very controlled conditions, controlled atmosphere, controlled temperatures. We can mimic real processes where you have pushing, smearing, rubbing kind of actions taking place. Oxide films on liquid metals, we can see their effect on spreading process and motion, on reactions. We can remove oxides and see what happens to the wetting and bonding situations. And we can study many unusual processes also using these kind of high temperature wettability tests. So with that, I conclude my presentation. I just want to show a slide, maybe one or two slides, mainly for students who are doing their graduate studies and doing some research. Quite often, and in fact, in most places, students have to publish their research in journals so that you actually share your findings with the broader professional community. And I want to bring up to the attention of students a journal that I edited called Journal of Materials Engineering and Performance. It is one of 6 journals published by American Society for Materials. Some journals of the society are jointly published by ASM and TMS, but this is fully owned by ASM. And ASM is a material society. I'm sure most of you know. It's one of the major societies of materials. The journal receives a lot of submissions. We get over 4,000 submissions a year. And currently, we are bringing out 78 papers in each issue every month. We have authored from 72 plus countries contributing. So we have a lot of papers coming in. And in fact, starting in January, we will be bringing out this journal bi-monthly. Every 2 weeks, you will have a journal issue with about 40 to 45 papers in it. So all papers go through a fairly rigorous review process. So if you have any good, interesting research results to present, excuse me, that you want to publish, you may consider this journal for your needs. Now, I'm not saying that because we don't get enough papers, we do get, but this is just to encourage young people to consider publishing in this journal. We also bring out special issues from time to time, and these are some recent and upcoming issues. So the announcements for these go out in ASM through different means. So we had additive manufacturing issue that was coordinated by my colleague, Bill Frazier. We have another additive manufacturing issue coming up in the next few months, space exploration, AM in space. NASA and JPL people are doing it. We are bringing out European Congress on Advanced Materials special issue. We had Professor Malay Banerjee helping with the surface energy engineering special issues. So we have a lot of different opportunities for bringing out special issues. And if you want to publish in special issues, you can do that. So with that, I say thank you, and I wish everyone good luck for your studies and research and scholarly activity. I go back to Dr. Patra, and if you have any questions from the audience, I'll be glad to answer.
Thank you, Professor Rajiv Asthana, for your such wonderful and delightful talk. There are so many new things that because I normally doesn't work in this particular field completely. Those who I work on specifically on mechanical alloying and sintering. Well, before I ask the participants to ask the questions, I have a little query that regarding during sintering process, what we used to do is that we do the mechanical alloying, and then we go for sintering, and specifically for liquid phase sintering, we have observed that this can lead to certain improvement in the densification. Now, sir, is there any chance that if we go for infiltration rather than liquid phase sintering, just infiltration during the sintering process, it will promote more densification rather than if we mix during mechanical alloying? Sir, can you put some light on it?
Okay, let me get back here. So you're saying that instead of trying liquid phase sintering, you want to infiltrate the system and see whether densification kinetics will be enhanced?
Yeah.
Is that the question you have? I'm not sure. I think infiltration may have some challenges, especially if you have relatively large size component, because infiltration will occur only through interconnected open ports. And that may limit the distance to which your liquid can penetrate the compacted or green part. With liquid phase sintering, of course, you have challenges in LPS because, as you well know, that when you have a liquid phase forming, upon cooling, you end up with solidification shrinkage and internal problems, cracking and metal stopped cavities. Those problems come. But liquid phase sintering also helps in more tightening, more compaction, better compaction, because like capillary forces will bring the powders closer together. So again, I don't work in this area, but my feeling is that perhaps infiltration might not give you the same quality of densified product as a sintered product. Again, this is something one has to try out actually to see whether it works, but that's just a hunch I'm speaking from. And the reason for that, as I said, was that a liquid from external source may have greater difficulty in penetrating throughout the bulk of your component.
Thank you, sir. Thank you very much.
Although I would mention one thing here, just to add that we know that in most powder metallurgy processes, even after sintering, when you have some residual porosity left, you are able to infiltrate and seal it with other things, right? So you have, for example, steel parts, you can seal the residual porosity with molten copper or with epoxy or other things. So that is possible. But during sintering, I'm not sure. That's a thing we'll have to try out.
Thank you, sir. Thank you, sir. So now I will request other faculty members, students, to raise their questions if anything is there. Any participants has any questions regarding today's talk, or anything that is coming in your mind, you can ask to sir.
Yeah, I know it is kind of late evening for everyone. Maybe it's dinner time, so
yeah,
might be
so
time for people to read.
Okay. So I think if there is no question from the participants, I'd like to thank Professor Asthana for giving us the time and present your talk. We are really privileged to be a part of the participants and to listen your such delightful talk. For giving us the time.
Yeah.
Thank you once again.
Thank you very much for the opportunity, and I wish everyone best of luck and hope our paths will cross again sometimes. Thank you. Goodbye, everyone.
Bye, sir. Thank you.